Hello everyone, my name is Nikhil and I work as Principal Architect in NCS Singapore. I am thrilled to be here today to discuss how we have leveraged EDA to address some of our clients' most complex challenges in the FSI sector. Before diving into the details, let me start by briefly introducing what NCS does. In NCS, our purpose is to advance our communities by partnering with government and enterprises to harness technology. We do this by bringing people together to make extraordinary happen. Combining the experiences and expertise of its 13,000 strong teams across 57 specializations, NCS provides differentiated and end-to-end technology services to clients with its next capabilities in digital, data, cloud, and platform, as well as core offerings in application infrastructure, engineering, and cybersecurity. NCS also believes in building a strong partner ecosystem with leading technology players, research institutions, and startups to support open innovation and co-creation. Our strengths are in government within Singapore. This is our differentiate. We are in unique position to leverage these strengths for commercial enterprises across Asia Pacific. Let's look at some of the fallacies of an EDA. This is not an exhaustive list. Events are always immediate. Event processing depends upon multiple factors like network latency, throughput of message broker, and system load. Delays are inevitable. Thus, events are immediate is a myth. We have to consider latency and timeout for critical events. EDA eliminates coupling. EDA gives a feeling that afferent and efferent coupling has reduced in the overall system, but it could introduce temporal coupling. Temporal coupling refers to situation where two or more systems, services, or components are dependent on being available or operating at the same time to successfully complete a workflow or exchange of information. Thus, we must embrace eventual consistency to let services operate independently and synchronize the state over time. We need to use well-defined transaction saga patterns to mitigate this. Event schemas will not change. Schemas are not static, but they do evolve, and mostly because of requirements evolve over time. So we must be mindful about the schema evolution. We may want to consider schema registry tools and design events for backward and forward compatibility. Scaling is always linear. Adding more instances of events consumer or brokers will not always improve performance proportionally. Bottlenecks still occur due to database constraints, network limitations, etc. Monitor and identify bottlenecks and design system with scalability in the mind. Let's continue with fallacies of an EDA. Event order is always maintained. Assuming event will be processed in the order they are generated is incorrect. Some brokers do not guarantee ordering. Ordering is often limited to partitions or topics, so the applications should be able to handle out-of-sequence events. Consumers are always up to date. Assuming consumers will always process events in real time is not right. Some consumers may lag due to the load, failure, or network issues. We have faced issues such as an event was received for processing before the dependent event was received much earlier was not processed by the service, thus making the new event wait for the previous event to process. But in the early implementation, the exception handling was not robust and the event was dropped. We need to have state recovery mechanism, implement idempotent processing and monitoring to detect lag to mitigate these kind of issues. Events are reliable by default. Believing that all events will always reach their intended consumer is a myth. Event delivery depends on the reliability of the messaging infrastructure, thus making messaging platform an important player in event-driven architecture. Failures such as dropped messages, misconfiguration, consumers downtime can lead to data loss. Use acknowledgement mechanism, durable queues, and retries for critical events. Employ dead letter queue to handle failure. The last but not the least, and my favorite one, EDA is always the best solution. EDA has trade-offs. It's not suitable for applications which require strict consistency or low latency in a tightly coupled process. So it's best to evaluate your needs before jumping into EDA. No discussion about EDA will be completed without transaction saga patterns. When we have an EDA, exception handling becomes critical, and thus comes the transaction saga pattern to help recovery. One of the most important things with EDA is to embrace asynchronous communication and eventual consistency. Even though we know this, implicitly we try to achieve atomicity and we bring the problems to ourselves. The table here shows the various patterns. As soon as we choose EDA, we have to understand that we are choosing the last four patterns because we consciously chose asynchronous communication. These are the four patterns which we can use when we choose event-driven architecture. We look at three parameters: communication, sync versus async communication, consistency, atomic versus eventual consistency, and coordination, orchestrated versus choreographed coordination. Choosing EDA means we have chosen asynchronous communication. Thus, this parameter is static in the 3D graph. Let's begin with fantasy fiction pattern. Here we have atomic consistency, asynchronous communication, and coordination is orchestrated. We typically increase the responsiveness of the system by making it asynchronous, but making a system asynchronous has its own trade-offs as the coordination becomes more complex. Because of the high level of coordination, the coupling level is extremely high in this pattern. Architects and developers must pay special attention to the out-of-order events and race condition. Another problem is this system will act like a monolith. If one of the services is down, the overall system is impacted because the coordinator will not be able to complete the atomic transaction. Because of these reasons, it is very difficult to scale this pattern. Moving on to horror story. This one is my favorite pattern because everyone comes across this pattern knowingly or unknowingly. If orchestrating an async transaction in atomic way was not fantasy enough, we expect it to be atomic and choreographed. Why it is called horror story? Because we expect atomic transaction with two loosest coupling styles, async and choreography. This pattern scales well because it does not have a coordinator or mediator, but it will have low availability because of the expectations of atomicity. But complexity of this pattern is very high as each service must track for atomicity. This is because of the fact that error handling conditions for this pattern is the most complex. Moving on to the parallel saga. This pattern embraces eventual consistency with orchestration. This pattern is suitable for complex workflows. Since we have mediator, the mediator becomes responsible for handling the error and sending an asynchronous request to compensate the failed transaction. The complexity of this pattern is low and coupling is also low. Scalability is high and availability is also high. This is all because we have embraced the eventual consistency in this pattern. The last one is anthology pattern. This pattern provides much higher throughput, but it makes each service bit more complex as it must track its own error handling and should be more context aware about the workflow. But if the workflow becomes complex, then this pattern will also become complex and will start having issues with data consistency. This pattern scales well and has high responsiveness and availability. Coupling is very low, but complexity is very high. When we work with our clients, they typically give us this non-functional requirement at high level. Applications should be active across data center to meet stringent requirement of real-time payments. In Singapore, the inbound fast payment needs to be responded back to automated clearing house within 5 seconds. Clients do want to use open standards rather than locking up with certain proprietary protocols. Recovery time objective should be less than 4 hours and even more stringent nowadays for real-time payments. Like in Singapore, the unplanned downtime of the fast payment cannot be more than 4 hours in a rolling year. Recovery point objective should be near zero for the applications. External out-of-the-shelf products should be able to connect to the platforms. Example, Swift Alliance Gateway An Alliance messaging hub should be able to connect to the message broker. Platform can support guaranteed messaging and sub-second latency for real-time payments. System should be available 99.99% of the time, and the system should be able to scale for future growth. These are all common requirements, and we can say these are not new, but with modern applications, which uses event-driven microservices architecture, the messaging platform becomes very important. To meet the requirement mentioned earlier, EDA needs a good messaging platform. Since banks use a range of applications, the message broker should be able to support multiple protocols like JMS, AMQP, MQTT, REST. Messaging platform should be able to support sub-second latency. And if the platform can support out-of-the-box connectors for legacy system to exchange data, then it is an added advantage as the companies don't have to build and maintain any connectors. Recovery point objective should be near to zero or zero for messaging platform. It should be able to support multiple messaging patterns like point-to-point, publish, subscribe, etc. Recovery time objective should be as low as possible. Some of the banks needs recovery time objective less than 20 minutes. We have worked with Solace on multiple projects from land, air, sea, public sector, and in financial services. Keeping the requirement of messaging platform in mind, we use Solace as the messaging backbone for our event-driven architecture. Setting up an active-active application across DC can be achieved using other messaging brokers, but we find that using Solace makes it easier. Solace supports open standard protocols and can also support multiple protocols like AMQP, REST, MQTT, JMS, etc. This plays a crucial role to ensure we can connect a lot of applications to the messaging platform to exchange data. We can get RPO equal to 0 across data centers. Very rare customers need this, but when they need it, Solace supports it. Indeed, if we talk about gap theorem here, we will lose availability, but in some cases, consistency is more important than availability. Another good thing about Solace is that the out-of-box micro integrations modules and connectors. Simple example would be to connect another messaging broker like IBM MQ and Kafka with Solace. Solace supports sub-second latency, which is required and desired in financial services industry. It does support message replay capability, just in case you need to replay messages again. Solace supports high availability with active-active and active standby pattern. The HA failover is very fast. We were able to failover within 45 seconds to the standby appliance. My colleagues in the next session will talk about using Solace in cloud as a software, but I will talk about how we have used Solace appliance in this session. In this pattern, producers, consumers, and Solace are active-active on both sides, and the Solace HA setup on each side is active standby. Producers on site 1 send messages to VPN X on site 1, and producers on site 2 send it to the VPN Y in site 2. The producers are the channels like e-banking, Swift, host-to-host, etc. Just in case for those who are new to Solace, VPN is nothing but a virtualization of an event broker into many individual virtual event brokers. So VPN X and VPN Y can be considered as two separate event brokers running on top of Solace appliance. The producers are configured to ensure in case of complete Solace appliance failure, the producer can send messages to the alternate site passive VPN which needs to be activated during failover. Example, in case the site 1 both the Solace appliance fail, then we need to activate the VPN X on site 2, and the producers on site 1 can keep sending messages to site 2 VPN X. This is an extreme case, but in general, if something happens to the active Solace appliance on the primary site, then the standby appliance, also known as mate, takes over in less than 45 seconds, and the producers can keep sending to the new active appliance on the respective VPN. The events from VPN X and VPN Y are bridged across to ensure applications running on both sides get all the events. We usually leave to the consumers to discard the events they are not interested in. But this filtering can be also done at the soulless appliance layer by ensuring queues subscribe only to the pattern they are interested in. Filtering on the soulless appliance level is extremely fast. This comes with a trade-off that if a change is needed in the filtering, then we have to update the filtering logic on the appliance. Not that big trade-off, but while making a design choice, we must explicitly consider this. With this pattern of design, we ensure that a specific customer or bank payment can be processed on specific site by a dedicated consumer. For this, on the broker, we created a dedicated queue for each customer or bank or group of customers or banks. We also ensure that the queues are marked exclusive so that only one consumer consume for sequential processing and the other consumers are on standby. The consumers can be configured to consume from specific set of queue or queues. This ensures that the consumers are processing the message in the sequence for specific customer or the bank where sequential processing is of utmost importance and isolate the issues for the customer bank in case they happen. In the POC, we also introduce some chaos to check the high availability and robustness and recoverability of the system. With the single touch automation, we were able to recover the system within less than 20 minutes. This pattern is like pattern 1. The only change is the producer and consumers are connected to Site 1 message broker. Site 1 message broker is set up in active standby mode. The message brokers on Site 2 are also in active standby mode, but no traffic flows there. In this pattern, we will, like pattern 1, get affinity of the customer or bank to a site and dedicated consumers to process the message in the sequence if needed. But in this pattern, it is less complex as the failure scenarios are reduced compared to pattern 1. The producers and consumers will connect to standby appliance in case active appliance fails. If both the appliance in site 1 fail, then the producers and consumers will connect to the appliance on site 2 after failover of Solus appliance is completed. This makes it a bit easier to manage in terms of recovery and automation script, but we don't use the Solus appliance on the alternate site, and thus this pattern requires regular DR activities to test the failover in case of an actual disaster happens. Moving on to pattern 3. This is very traditional setup of the application using Solus appliances. All the producers and consumers are producing and consuming messages to a single VPN. Everything is like pattern 2, just that instead of 2 VPN, a single VPN is used. It's very simple and very easy to manage. The failover is very easy, but not optimal use of all the resources which has been provisioned, especially the Solus appliance which are sitting and doing nothing on the alternate side. That's all for today. Do reach out to us to explore how NCS can help you with the EDA journey. Thank you.